Hello everyone, this is part 2 of the trigonometric limits video. If you're here for the first time, I highly recommend checking out part 1 where I introduce how to solve these types of problems. And in this video, we're going to go over some harder limits involving trig functions. So first of all, to approach this problem, I want to point out that the limit as x approaches 0 of tangent x over x is 1. I proved that in part 1, so you can go ahead and check out part 1 to see that limit. So anyways, I'm going to use this, and also the fact that limit as x approaches 0 of sine x over x equals 1. And this also I explained in part 1, and I recommend just memorizing these and having them with you when you're doing these types of problems. So to start off, I'm going to split this fraction. Now, to deal with this, I'm going to try to match these arguments so that I can use this fact. So I'll go ahead and do this. I'll factor out 1/2. I just took this 1/2 out from here, and now what I'm going to do is multiply the entire fraction by 3. Now you'll notice that these two arguments are the same, so all of this equals 1, so just 3 over 2. Then I'm going to split this like so. So this is equal to 3 over 2 plus the limit as x approaches 0. And then for this, sine 5x over 2x. And then this sine 5x over x. This guy, I am going to multiply by, hold on a sec, let's see. So I'm going to factor out this 2, or this 1/2, sorry. And then I'm going to multiply everyone by 5. And this limit equals 1, so that's 5 over 2. This is 5 over 2. And using the same logic here, that's 5. And using this same method, this ends up being 5 too. So this is 3 over 2 plus 25 over 2, and that is 28 over 2, aka 14. So the next example I have here is kind of in that form of sine x over x, but you'll notice that we have x minus pi over 3, and the limit is approaching pi over 3. So I want to show you the graphs of these functions real quick. So if you'll notice, I have sine x over x and sine x minus pi over 3 over x plus pi over 3. Sorry, x minus pi over 3 over x minus pi over 3 graphed. So this is what they look like around x equals 0, and x equals pi over 3 should be somewhere around here. If we shift the graph of sine x minus pi over 3 all over x minus pi over 3 to the left, what we'd have to do is we'd have to add pi over 3. Remember from shifting functions from earlier coursework. If we shift this function pi over 3 to the left, we add pi over 3 here, but then we subtract pi over 3 from the limit. So what I remember is just, if I add in this expression, I subtract the same thing from, if I add to x in this expression, I subtract the same thing from x here. If I subtract from x in this expression, I add to x here. So I'm going to shift left by pi over 3. So first of all, I am going to subtract by pi over 3 to the left here. And then in this argument of x, I'm going to add pi over 3. Negative pi over 3 plus pi over 3, that's 0. So just sine x over x, and that's 1. Now for this function, I'm going to have to introduce the squeeze theorem. The squeeze theorem states that if f of x, a function, can be bounded in between two functions, g of x and h of x, if the limit as x approaches some number of g of x is equal to the limit as x approaches that number of h of x equals some limit, then because f of x is bounded in between these two, the limit as x approaches that number of f of x equals L. Even if we have an indeterminate form in x and we're not able to find it, if we're able to use the squeeze theorem and we know we can bound x, then we can do this. So I'm going to show you guys how to apply the squeeze theorem here in this problem. So we've got the limit as x approaches 0 of x cubed sine x minus pi over x. Try this out and you get 0 over 0 as usual. And the first thing I'm looking at is this sign. This is simply just sine of x minus pi. And remember that the range of sine is always -1 to 1. The values that you get from sine will always be in between -1 and 1. What does that mean? Let's just take any theta. That means that sine theta is between -1 and 1, right? Well, why can't we apply that same logic to x minus pi? Now, we've got a function bounded in between two functions, which are just -1 and 1, just constant functions. Let's try to get this expression and bound it in between two things and take the limit of the endpoints and get that limit by the squeeze theorem for what's in the center. Right, so you might be thinking multiply by x cubed and divide by x, but you can't do that. And the reason is because we cannot have the possibility of multiplying a negative number when we have an expression that's an inequality like here. Like I am not allowed to multiply both sides by a negative number. If I were to, I would have to open up two different cases and try each one a separate way, and that's just no need to do that here because there's a quick little shortcut we can take. Why don't we multiply both sides by x squared? Because that is a guaranteed to be positive number. Power is even, x squared looks like this. Keep in mind that x cubed looks like that. So x cubed could potentially have negative values as well as x2. But x squared always has positive values. Anyways, change what's in the center here. X squared is equal to x cubed over x. So there, that's how we got back to the function we started with. Then now I'm going to take the limit of these two endpoints and see if they're equal. Limit as x approaches, we're talking about 0, right? So limit as x approaches 0 of negative x squared. Does that equal the limit as x approaches 0 of x squared? Yes, it does. That's actually equal to 0. So therefore, by the squeeze theorem, the limit as x approaches 0 of x cubed sine x minus pi all over x is equal to 0. So that's the squeeze theorem for you. Now, another similar squeeze theorem problem. Here we have x sine 1 over x. Now, first of all, I'm going to say that sine of 1 over x will always be bounded in between -1 and 1, no matter what, because we just have sine of something. Now, remember, as I said earlier, I can't multiply both sides by x. Why? X has a possibility of being negative. Now, I want to make a quick note here. If we were talking about the limit as x approaches 0 plus, like the limit when x approaches 0 from the right, from the positive, all values will be positive. We could multiply by x, but x approaches 0. So actually what I'm going to do is I'm going to multiply by absolute value of x. I know that's positive, right? So negative absolute value of x, that's negative x. Absolute value of x times sine 1 over x, that's absolute value of x times sine 1 over x. Absolute value of x, that's absolute value of x. Now, let's take the limits. You might be wondering why I'm taking the limits a little early, even though this expression doesn't look like this one. Well, I can say with confidence that the limit as x approaches 0 of, and for absolute value of x over here, the limit as x approaches 0 of absolute value of x is 0. If you remember the absolute value function, it looks like this. So then by the squeeze theorem, the limit as x approaches 0 of absolute value of x of sine 1 over x equals 0. And now we can say that the same goes for the limit as x approaches 0 of x sine 1 over x, because as absolute value of x approaches 0, x does as well. Essentially what I'm saying is that the limit as x approaches 0 of absolute value of x is definitely equal to the limit as x approaches 0 of x, and that's 0. So, limit as x approaches 0 of absolute value of x times limit as x approaches 0 of sine 1 over x, that's equal to 0 by the squeeze theorem, which we found earlier. I'm going to take this, substitute this in for this. Limit as x approaches 0 of x times limit as x approaches 0 of sine 1 over x. And there we are, our expression, and that equals 0. Now, remember, don't multiply the inequality expression by something that has the potential to be negative. Otherwise, if you wanted to, you would have to open up the two signs and flip the signs. Remember, multiplying or dividing by negative causes you to flip the sign in an inequality. So the next example here that I have is the limit as x approaches 0 of cosine x minus 1 over x. Now, don't get tricked by this and think that it's this. No, this is not this. So I'm going to multiply by the conjugate first. Cosine squared x minus 1, that's sine squared x. Hold on, wait, sine squared x plus So cosine squared, or sine squared x equals 1 minus cosine squared x. And sine squared x equals 1 minus cosine squared x. So I'm going to say that this is cosine squared x minus 1 all over x times cosine x plus 1. And then what I'm going to do is I'm going to take this, factor out a negative. Then this is sine squared x. Take out that negative sine squared x over x, or sorry, I'm going to take out, so I'm going to say this equals sine squared x. I'm going to split this fraction like this. Right, so sine x times sine x is sine squared x. The negative that we have is here. This x is here. This cosine x plus 1 is here. So this equals negative 1. And then this equals negative 1 times plugging in 0 over 2. So we've got two more examples here. Limit as x approaches 1 of sine 3x minus 3 over 2x minus 2. And this guy. So first things first, I'm going to multiply everything by 3 over 2 by 3 over 2, because that is going to match these, it's going to get these arguments to match, times 3 over 2, and then all that is over . So basically, in the numerator, multiplied by 3 over 2. In the denominator, multiplied by 3 over 2. 3 over 2 times 2x minus 2. That's 3x minus 3. I'll show you that quickly in case. Got lost there, but 3x minus 3. And notice that these arguments now are the same, but I'm approaching 1, not 0. So I can't use sine x over x. Factor this out real quick. What I'm going to do is I'm going to shift this once again. I need to get this to be 0. So if I'm subtracting 0 there, subtracting 1 there, I have to add 1 here. So that's sine 3x minus 2 all over 3x minus 2. And what does that equal? 3 over 2, because these are the same. This is 0, that's 1. Finally, for the final example, I'm going to, first of all, we're approaching 0 plus. I'm going to use the properties of logarithms. So ln of f of x minus ln of g of x. That is equal to ln of f of x all over g of x. That is a property of logarithms that I'm going to use here. So then it's ln of sine 2 theta over tangent theta. Now I'm going to use the trigonometric identity that sine 2 theta equals 2 cosine theta sine theta, or sine theta cosine theta. And then tangent theta, I'm going to rewrite that as sine theta over cosine theta. Move this cosine up here. Cancel out these signs. And that becomes the limit as theta approaches 0 plus of ln of 2 cosine squared theta. Now, remember that the graph of y equals ln x looks like this. It's only defined on 0 to infinity, not including 0. So cosine when you're approaching 0 from the positive direction and the negative direction is positive, because cosine takes positive values in the first and fourth quadrants and negative values in the second and fourth. So there's no issue about us approaching negative values of 0 and therefore the limit not existing, because it's ln of something. So, oh, and also it's squared, by the way. So there's just not that possibility at all. So its limit as theta approaches 0 plus of ln of, we can go ahead and use direct substitution of 2 cosine squared of 0, and that equals ln of 2, because cosine of 0 equals 1, cosine squared of 0 equals 1, so 2 times 1 ln of 2. Thanks so much for watching. If you found this video useful, please consider liking or subscribing. And if you have any questions or comments, feel free to drop a comment. Thanks so much.